Hypermedia types. Hypermedia types are a class of media types that are usually text-based and contain links to other resources. By providing links within representations, user agents are able to navigate from one representation to another based on their understanding of the meaning of the link. Hypermedia types play a huge role in decoupling clients from servers. Through hypermedia, clients no longer need to have pre-existing knowledge of resources exposed on the web. Resources can be discovered at runtime. Despite the obvious benefits of hypermedia in HTML for web applications, hypermedia has so far played a very minor role in the development of web APIs. Web application developers have tended to avoid hypermedia due to lack of tooling, a perception that links create unnecessary bloat in the size of representations, and a general lack of appreciation of its benefits. There are scenarios where the cost of hypermedia cannot be justified, for example, when performance is absolutely critical. For performance-critical systems, the HTTP protocol is probably not the best choice either. When evolvability is a key goal in an HTTP-based system, hypermedia cannot be ignored. Media type explosion. So far we have seen how generic media types require out-of-band knowledge to provide semantics. And we have seen examples of more specific media types that carry domain semantics. Some members of the web development community are reluctant to encourage the creation of new media types. There is a fear of an explosion of media types, that the creation of a large number of new media types would produce badly designed specifications, duplicated efforts, and service-specific types, and any possibility of serendipitous reuse would be severely hindered. It is not an unfounded fear, but it's likely that, just as with evolution, the strong would survive and the weak would have little impact. Generic media types and profiles. There is another approach to media types that is favored by some. Its basic premise is to use a more generic media type and use a secondary mechanism to layer semantics onto the representation. One example of this is a media type called Resource Description Framework (RDF). To dramatically oversimplify, RDF is a media type that allows you to make statements about things using triples, where a triple consists of a subject, an object, and a predicate that describes the relationship between the subject and object. The significant portion of the semantics of an RDF representation are provided by standardized vocabularies of predicate that have documented meanings. The RDF specification provides the way to relate pieces of data together but does not actually define any domain semantics itself. In example 6-8, taken from the RDF Wikipedia entry, the URI http://perl.org./dc/ elements/1.1 refers to a vocabulary defined by the Dublin Core Metadata Initiative. Example 6-8. Road. F example. XMLNSDC equals http://perl.org/elements/1.1/. Tony Benn. Wikipedia. Another example of layering semantics is the use of application-level profile semantics. PS is a method of specifying domain semantics that can then be applied to a base media type like XHTML, as shown in example 6-9. B. Recently ratified link relation profile is a way of attaching these kinds of additional semantic specifications to existing media types. Example 6 to 9. ALP. S over X HTML get / some mystery resource 200 OK content type application / X HTML content length 29. % of requests with their cache control max age value in days. From to days. % 0. 59. 0. 1. 13. 1. 30. 17. 30. 365. 8. 365. 3. Get http / example.org / profiles / stats 200 OK content type application / ALPS. Types to support the domain of statistical data. A data point. X value on graph. Lower bound on X range of values. Upper bound on X range of values. Y value on graph. Lower bound on Y range of values. Upper bound on Y range of values. The hypermedia application language HAV, demonstrated in example 6 to 10, is a generic media type that uses link relations as a way to apply domain semantics. Example 6 to 10. H. And in both application / Halsm and application / Halsson. Title equals % of requests with their max age value in days. Y value equals 59. XLOSA value equals 0. XUPPER value equals 0. Y value equals 13. XLOSA value equals 0. XUPPER value equals 1. Y value equals 17. XLOSA value equals 1. XUPPER value equals 30. Y value equals 8. XLOSA value equals 30. XUPPER value equals 365. Y value equals 3. XLOSA value equals 365. XUPPER value equals 65535. Zaxistic range, Yaxistic %, title % of requests with their max age value in days, embedded. http / example.org /stats / data point. Y value 59. XLOSA value 0. XUPPER value 0. http / example.org /stats / data point. Y value 13. XLOSA value 0. XUPPER value 1. http / example.org stats / data point. Y value 17. XLOSA value 1. XUPPER value 30. http / example.org stats / data point. Y value 8. XLOSA value 30. XUPPER value 365. http / example.org stats / data point. Y value 3. XLOSA value 365. XUPPER value 65,535. HAL relies on link relations to provide the semantics needed to interpret the non-HAL parts of the representation. This means that in the documentation for the link relation type http://example.org/stats/data point, the meaning of y value, xlosa value, and xupper value needs to be defined. HAL doesn't care whether these values are specified as attributes or elements. It is up to the consumer of the HAL document to discover where the information is stored. One challenge with using the link relation to communicate semantics is that entry point URIs often do not have link relations. When you type a link into a browser address bar, there is no link relation. There are a couple of workarounds for this. You can keep the root resource limited to just embedded resources and links, or you can use a link with the link relation type to associate semantics to the root resource. The advantage of using a generic media type is that tooling to generate, parse, and render those formats likely already exists and can be reused. It also means that you can define semantic profiles that have mappings to multiple different base media types. This can be advantageous when one particular media type is more suitable for a particular platform. When defining domain-specific media types, if it is desirable to support both XML and JSON variants, you must write two specifications because the format and semantics are both defined by the media type. Efforts are underway to try to formalize the process of describing a semantic profile, and it is likely that there will be multiple viable approaches. The disadvantage of using the generic media type combined with a secondary semantic profile is that the semantics of the message are less visible to intermediary components. Media types specified in the content type header can easily be processed by any layer in the HTTP architecture. Using techniques like link relations and profiles to attach semantics makes it more difficult for intermediaries to discover that information and make processing decisions based on it. As is commonly the case in web architecture, there is not only one way to do things. There are advantages and disadvantages, and systems must be engineered to meet the requirements. The use of a secondary semantic profile is definitely an interesting space to watch, and I look forward to a future where there are more prescriptive solutions to defining the semantics of a message. From these examples, you can see there are many ways you can communicate the same data between the client and server. Some media types carry more semantics, some less. How much application-specific semantics you use to drive your client depends on the availability of existing standard media types that suit your needs and your tolerance for coupling. Other hypermedia types. The last few years have seen a number of new hypermedia types introduced. The following sections summarize a few examples. Collection JSON. The collection JSON media type addresses the domain of lists of things. It is interesting in that it is generic and specific at the same time. It specifically supports only lists of things, but it does not care what the list of things is. It also has interesting semantic affordances that can describe how to query the list and add new items to it. Although it has minimal semantics for the items in the list, it does support the notion of profiles for describing the list items. Siren. Siren is another fairly new hypermedia type that is similar to HAL in that it is effective in representing nested data structures and embedded resources. It differs from HAL in the way it attaches semantics to data elements. Siren borrows the notion of a class from HTML as a way to identify semantic information. It also makes a distinction between links that are for navigating between resources and those that represent behaviors. The action links also have their own style of link hints that describe to the client how to invoke the action. Although some people argue that we should all just standardize on a single format, I would rather let natural selection take its course than try to force-fit a single hypermedia format into every scenario. HTTP makes it easy for APIs to support multiple representations of a resource, and clients can pick the one they prefer, so having multiple formats in use is not a major hindrance to progress. Up to this point, we have talked primarily about media types as a way of communicating semantics, but as we hinted when discussing how, semantics can also be communicated via link relations. The next section will discuss this further. Link relation types. In the introduction to this section on contract types, I noted that link relation types suggest why you might be interested in a particular resource. Link relation types were first introduced in HTML. The most common link relation type is probably the rel equals styler sheet value, which connects an HTML page to the styler sheet used to help render it. More recently, there has been an effort to fully specify what a link relation type really is. This results of this effort can be found in RFC 5988. Semantics. In the same way that media types can be very generic about the semantics they communicate, so can link relations. There are some standardized link relation types like next, previous, current, item, collection, first, and last that are very generic. However, they do provide important contextual information about the related resource. On the other hand, there are some standardized link relations that have very specific usages. Examples of these are help, monitor, payment, license, copyright, and terms of service. Reviewing the standard registry of link relations only hints at the power of link relations. Most of the standard link relations do not define any behavior or constraints. They simply identify the target resource or describe the relationship between the context resource and the target resource. Politics. If you spend any amount of time reading about the world of web and internet-specific cations, you will quickly learn there are lots of politics involved in the process. I will warn you that I am biased in favor of the Internet Engineering Task Force (IETF) as the keeper of Internet-related specifications. The IETF defers to IANA for registries, which is why I refer to the IANA Media Type Registry and IANA Link Relation Registry. However, there are other organizations that are unhappy with the IETF/IANA registration procedures and have chosen to use an alternate registry for link relations. A few link relations have begun to suggest we can do more with them than just identify a relation. Consider Norfera and Preach. Norfera tells the user agent that if it follows the link, it should not specify the referrer header. Preach tells the user agent that it should retrieve the target resource prior to the user requesting to follow the link so that the representation will already be in the cache. In these cases, the link relation is actually instructing the user agent about how the server would like it to interact with the link. These instructions can go much further. A link relation type specification could indicate that only the post method should be used with a particular link, or that when the link is followed, the returned representation will always be application/JSON. Instead of defining interaction mechanisms in a specification, some people prefer to embed metadata into links to describe to the client how to interact with the link. For example, an HTML Tag has a method property that indicates to the browser whether to use a get or post method. A variation on this is the use of link hints, which allow a server to embed metadata that suggests how a link might be used. It does not preclude there being other valid ways of using the link. All these approaches are valid ways to communicate link mechanics to a client. Using embedded metadata with a fairly general link relation is the most reusable approach but requires the most bytes over the wire. It also potentially reduces the number of link relations of which a client needs to be aware. Using a precise link relation with all the details of the interaction specified in the documentation is more bandwidth friendly but puts more requirements on the client application. If we take this idea of a precise link relation to an extreme, a link relation address could require the use of the get method and return application /some with properties street, city, state, country, and zip code. The more constrained the link relation, the less reusable it becomes. And it is highly unlikely that such a link relation would be accepted by the subject matter experts who manage the registry. However, there is the notion of extended link relation types, where you use a URI as an identifier to uniquely identify the relation. When using an extended link relation type, you are not required to register the link relation with IANA, and you are free to do what makes sense to you. The interesting effect of using a link relation to precisely describe the expected response is that it allows the use of generic types like application/XML and application/JSON to convey data without depending on out-of-band knowledge. However, my personal experience has been that dividing the semantics between link relations and media types more evenly produces more reusable contract types. Link relations and media types work together in a manner similar to how adjectives and nouns work in language. The adjective happy can be used in combination with many nouns. By combining the independent adjective and noun, we can avoid the need for an explosion of nouns such as happy dog, happy cow, happy fish, and so on. Collection Version 1.0 Ref http://example.org/journal/ from date equals 201309121 to date equals 201309222. Items Ref http://example.org/transaction/794 Data Amount 14576 Currency USD Date 2013091 Links Real origin Ref http://examples.org/account/bank1000 Real destination Ref http://examples.org/account/payables/Hawaii travel Items Ref http://example.org/transaction/794 Data Amount 150,000 Currency USD Date 201309222 Links Real origin Ref http://examples.org/account/receivables/acme Real destination Ref http://examples.org/account/bank1000 As an example, imagine that we are to register two link relation types, origin and destination. There are many scenarios in which we need to represent where something has come from and where it is going, whether it is a file copy, a bank transfer, or a route on a map. The same link relations can be reused in many different scenarios. Sometimes the semantics of these reusable relations are sufficient to implement generic function ability on the client regardless of what the links may be pointing to. This is very similar to the way polymorphism works in object-oriented development. Usually when people think of links in hypermedia documents, they think about defining relationships between domain concepts. This is the primary use of links in the field of linked data. However, it is possible to use links for much more than making declarations about the relationships in our domain.